Computer. Good. Today is March 10, 2025, 9:42 p.m. And I'm going to start sharing my screen with you. Here's the syllabus, the schedule, right? Just to make schedule in the syllabus, we finished chapter 19 on the chapter 19 covered electric potential, and also it covered capacitance. And now what we're going to do, we're going to start on electric circuit. It's a very important, electric circuit is a very important topic in electricity and magnetism. If you want to know how your cell phone works, if you want to know how a light bulb works, if you want to know how any circuit works, you have to master the topics that we're going to cover in this chapter. And this is just the tip of the iceberg. Okay, what we're going to cover here is just the tip of the iceberg. But those are the very basic concepts that you need to understand any electric circuit. Electric and electronic circuits. And let me show you the book right in here. Wait a minute, that's not the one. The real one is this one right here. Okay. Okay, electromotive force and current, that's what they are going to talk about. So let's switch to my notes. Insert, page break, 10th of 2025, Monday. Let's take a look again at the syllabus, right? Because we're going to have an exam soon, coming very soon, right? It's going to be next week, the exam. Our next holiday is going to be at the end of the month, 31st of March. And then we have the spring break here. So let's see. The exam, what we are going to do for now, chapters here for the exam, chapters 18 through 20, okay? Chapters 18 through 20. That's what the exam is scheduled for. Wait a minute. Well, for now it's 18 and 19. Let's see if we have time to cover 20 as well. Most likely we won't. But let's stick to 18 and 20 for now. And don't forget the lab too, the lab 1 will be part of the exam as well. And this thing here shouldn't be here. 19, lab 1. That's where it should go. More students are coming. Here you go. And lab 1 is due the day after tomorrow. Electric circuits. Okay, now we can. The first thing that you have to know about electric circuits is, that's week number 4. Week number 4. Actually, week number 5, right? Week number 5. Okay, electric circuits. First thing you have to know about electric circuits, first thing you have to know about electric circuits is the idea or concept, right? Or concept of electromotive force. Electromotive force. It's not a, in electric circuits, we use a source of electromotive force, to power the circuit. By the same token that the engine of your car is used to power your car, we also have something, an engine, right, between quotes. That's an electric engine that's used to power an electric circuit. Let's put it this way. By the same token that the engine of your car is used to power your car, we also have an engine to power an electric circuit, And I don't like this way to state that, but that's okay. Okay, let's use what the book is used. Our book uses this expression. Okay, electromotive force. I don't like the expression of electromotive force. Okay, I don't like it. But since every book uses it, let's use it as well. By the same token that we have that the engine of your car powers your car, we also have an engine that powers an electric circuit. And this engine is called a source of electromotive force. Okay? The most common source of electromotive force is the battery that we have out there. There are other sources of electromotive force, okay? But the simplest one is the battery, and anybody can buy a battery out there. It's the battery. There are all sorts of batteries, and there are all sorts of batteries. We have batteries of 1.5 volts. The most common is a battery of 1.5 volts. Then we also have batteries of 9 volts. We have batteries of 12 volts. The battery of your car is a battery of 12 volts, a source of electromotive force, and so on. And then you can create and then you not just a battery, but also and so on, right? In addition to batteries, we also have the power supply, the same device that we are using in lab number 1, okay? The power supply is a fancy battery whose electric potential can be adjusted, okay? It's a fancy battery with, let's put here, with an electric potential that can be adjusted. Let's put this way. That can be adjusted. And I already showed to you that we can buy those those power supplies out there. Okay. And when we say that a battery, right, powers a circuit, what do I mean about that? You know, they are actually powering specifically what they're powering. Specifically, they are powering the electrons in the electrons that are in the circuit. That's what the source of electromotive force does. You know, a source of electromotive force, makes the electrons in the circuit make the electron move, right? Make the electron move in a circuit. That's what the whole idea of electricity is all about. That's always called electricity, right? Electricity comes from the electron. The word, note that the word electricity comes from the electron, which is the particle that moves in the in general, not right? We can, you know, which in general, right? In general, the particle that moves in a circuit. It's not 100% true because we can get other types of circuits out there in which an ionic atom can move in the circuit as well as possible, okay? But the circuit that we're interested in is the one that uses metals, wires, okay? And we can go ahead and, you know, here you go. Electric circuits here you go. Electric circuits are best realized using metals, okay? But again, you know, that's not the only type of material that can be used in a circuit. We can use ionic solutions to form electric circuits. Plasma in space can also form electric circuits. But the best one that we are going to concentrate on are the electric circuits that we use with metals, metallic cables. The one that we have at home, copper cables. Okay, but the copper is not just the only one that's used in an electric circuit. That there are other metals, okay? But copper is the best one because not only is cheap, but it's a very good conductor as well. But we can also use gold, like we can use iron, we can use aluminum in an electric circuit, we can use silver, okay? And silver is an even better conductor than copper, by the way. When I mean better conductor, you mean we have less losses. But the problem with silver is that it's too expensive compared to copper. That's the problem. Okay, that's the problem with silver. Copper is a better conductor compared to gold, okay? Gold can be more expensive than copper, but copper is a better conductor than gold. It's very difficult to find a metal that conducts as well as copper and silver. It's very difficult. And I want you to have an idea, you know, a model in your head how these circuits work. Okay. So here you go. And others are partially made of almost free electrons. Okay. Electric circuits are best realized using metals such as copper, gold, iron, aluminum, silver, and others. Nowadays, people are using a lot of aluminum, okay, in the place of copper. Aluminum is not as good a conductor as a copper, but we are using aluminum because aluminum is very light, okay? And we use those metals because they are made partially. They're made up partially of free, almost free electrons. Let me emphasize here. So now we're looking at the microscopic constituents of those metals. They're made almost of free electrons, and I'm going to the so-called valence electrons. Remember that? You must have learned that in chemistry. The so-called valence electrons, which can move from one atom to another one easily, okay? They only move from one atom to another one. They don't escape the surface of the metal, but they have this facility of moving easily from one atom to another. That's why we can produce a current. That's why we use metals in our electric circuit. Okay, if there is no power source applied to these valence electrons, they move in an almost random fashion from atom to atom. However, if we apply a source, a battery, right? A battery to this metal, the electrons will move in a specific direction in our circuit. Let me get one drawing here for you, my illustrations. Okay, illustrations are very good to grasp concepts, okay? That's why we use it. So let's start with my electric circuit here. Before we get actually in electric circuit, we have to review the concept of an atom, right? That's a very good model of an atom. The model of an atom is very similar to the model of the solar system, with the sun in the center and the planets orbiting the sun, okay? In this case, the sun in this case would be the nucleus of the atom. The nucleus of the atom is made up of protons and neutrons, which are much heavier than the electrons that surround it, okay? That's the concept that you have to keep in mind. An isolated atom is just like that. It's just like that. You know, you have inner electrons and outer electrons. The outer electrons, the ones that are further away from the nucleus, are the so-called valence electrons. Valence electron, let's see. No, it's not valence electrons. We gotta write down here model of an atom, right? Model of an atom. Outer, and then we, outer electrons in an atom. The outer electrons in an atom are the so-called valence electrons. Okay, so a valence electron would be this one right here. Would be this one right here. Okay. And they are very important, those valence electrons. Valence, oh, here you go. Valence electrons are easier to extract from an atom. Valence electrons are easier to extract from an atom because they are not so tightly bound. Okay? So that's an atom in that's how an atom in, let's say, suppose that we have a single atom in the universe. That's how it looks like. Okay? But then when we put a bunch of those atoms together, okay, like making a solid metal, like a piece of an iron of a piece of iron, or a cable of copper, what we end up having is a bunch of those atoms. I didn't draw the electrons here, okay? They're put together and they're very orderly, okay? They're very orderly. And in the case of an isolated atom, we have those electrons, and if you have an isolated atom, this electron is not easily extracted from the atom, okay? However, things start to change when we put an atom very close to each other. Okay? When we put an atom very close to atoms very close to each other, what's going to happen? Those valence electrons, they move rather easily from one atom to another, okay? In a random fashion. Okay? In a solid, valence electrons tend to be shared among atoms. They jump from one atom to another in a random motion. Okay? Here are my electrons moving from one atom to another. Can you picture that? Maybe I should draw a small electron here. Let's do that. Negative, right? I'm going to make it smaller. The positive charges, they don't do that because for two reasons. Not only they're very heavy, they're 2,000 times heavier than the electron, but they have a binding energy that's very large. It's very difficult to extract protons from the nucleus. It requires an enormous amount of energy. Plus supposed to represent, okay, the plus is supposed to represent the protons, right? The protons has a positive nucleus, remember? The nucleus of an atom is made up of protons and neutrons. And the positive that you see here refers to the positive electric charge, okay? By the same token that the negative here refers to the negative electric charge of the electron, okay? So if I want to be more, here you go. Through, right? I'm gonna put an electron here in every one of those arrows to show that the electron is moving from one atom to another one. Here you go. And so on. Okay. So do you see the difference, right? So let's write that down here now. Let's look at step by step how an atom works, right? Let us look step by step how an atom works. Okay, one, an isolate atom is made of a nucleus, of a positively charged nucleus, which by the way is very small, okay? Which is very small in size, with a very small size, okay? The nucleus is made of protons and neutrons. It's made of a positively charged nucleus, which is very small in size, okay? And depending on the atom, right? And several electrons orbiting the nucleus, okay? Let's not forget the nucleus is made of protons and electrons. Of positively charged protons and neutrally charged electrons. Okay, what else you have to know? Although the mass, the charge of the proton has the same magnitude of the charge of the electron, comma, the mass of the proton is almost 2,000 times higher than the mass of the electron. Remember that? Remember that, okay? To be more precise, you know, it's 1,800 times higher. To be more precise, it is 1,800 times greater, right? Greater. The neutron is the same situation. The neutron too. The neutron too has a mass that is roughly 1,800 times greater than the mass of the electron. Okay? And several electrons orbiting the nucleus. Okay. What else you have to know? The electrons that are further away from the nucleus, are called the valence electrons. Okay, valence electrons are very important because they can be extracted very easily from the nucleus. Okay, remember the valence electrons. Can be extracted more easily, right? Not very easily, but more easily from the nucleus if compared with the other electrons, Compared with the other electrons, okay? Now, that's for an isolated atom, okay? That's for an isolated atom. When you put several isolated atoms, several atoms next to each other, okay, comma, the atom start to behave, the valence atom, the valence electrons of the atoms start to behave slightly different. Okay? And what do I mean by this start to behave slightly different? The atoms start to share their valence electrons with each other. Okay? Keep that in mind, that illustration that I drew for you. Okay? We start to share, okay, the valence electrons with each other. If no power source is applied to these atoms, okay, this atom, comma, the valence electrons will move from one atom to another in a random fashion. in a random fashion. However, if we apply a source of electromotive force to a metal, which by the way is a combination of a very large number of atoms, then all these valence electrons will start to move in a specific direction. Okay? That's what you have to. Let's see if I have, here go. I have here my metal, right? Illustrated here. Here you go. Here's my metal. But then now I got my metal bar and I connected it to a battery, okay? That's the symbol of a battery. Very similar to the symbol of the capacitor. The difference is that the battery has a shorter bar, right? It's two bars, right? The capacitor is two lines, just like this one. The difference between the battery and the capacitor is that the battery has a shorter line, okay? That's the symbol of the battery. The shorter line corresponds to the negative terminal of the battery. The longer line corresponds to the positive terminal of the battery. And now keep that in mind. You have this metal bar, and I connect one end of the metal bar to the negative terminal of the battery and the other end of the metal bar to the positive terminal of the battery. What's going to happen here? The positive terminal of the battery is going to attract the negative charges of the metal. Make sense? And those electrons that are attracted are the valence electrons, which keep on jumping from one atom to another one. Okay? That's the picture that you must have it. Between this terminal of the battery and this other terminal of the battery, we have an electric potential difference. And the value of the electric potential difference is going to depend on your battery. If it's a 1.5 volt battery, the electric potential difference between those two terminals is going to be 1 volt and a half. If it's a 9 volt battery, the electric potential difference between those two terminals are going to be 9 volts, and so on. Okay? You get this idea? And now that my electrons are moving here in the circuit in a specific direction. Now we have what we call a current, an electric current, a current of electrons. And the word current is related to motion, okay? A motion of electrons in a specific direction. Okay, by the same token that this positive terminal of the battery attracts the negative charges, this negative terminal of the battery is going to repel, right, the negative charges. Okay, so let's see. So here you go. When you put several atoms next to each other, the valence electrons of the atoms start to behave slightly different. And the difference in behavior is that the atoms, they start to share their valence electrons with each other. If no power source is applied to these atoms, the valence electrons will move from one atom to another in a random fashion, back and forth, you know, vibrating from one atom to another. However, if we apply a source of electromotive force to a metal, which is a combination to a metal, which, by the way, the metal is a combination of a very large number of atoms, then all these valence electrons will start to move in a specific direction. Okay? And the specific direction, this specific direction corresponds to the positive terminal of the battery. Okay. And then I'm going to put that, okay, here you go. I'm going to do this way. This is a specific direction correspond to the positive terminal of the battery. So electrons move towards the positive terminal of the battery, right? Not only that, electrons also move away from the negative terminal of the battery. And there is one more thing. Yeah, go ahead, Bianca. You have a question? Did you raise your hand, Bianca? You want to ask a question? Okay, looks like Bianca didn't raise her hand, right? So electrons also move away from the oh, okay, okay. Your cat stepped in your computer keyboard. Okay, good. And what else you have to know? You know? Once electrons reach, one more important thing that you have to know. You have to have this model in your head so you can understand how an electric circuit works, right? Once electrons reach the positive terminal of the battery, okay? Something interesting happens. If the battery is still charged, okay? In other words, if the battery is still charged, if it still have some energy, right? The battery itself will separate these valence electrons from the positive charge, from its positive terminal. That's how a battery works, okay? From its positive terminal. You can picture, you know, that a battery is nothing but a battery is like a chemical power plant. Can you keep that in mind? It's like a chemical power plant capable of separating the negative charges from the positive charges, capable of separating the negative charges, right? Let's put here the negative charges from the positive ones. Okay? So the idea goes just like that. He goes, if you were able to see inside the battery, right? And if we were able to come up with a very powerful microscope and see inside what's happening to the inside of the battery, I'm gonna need this guy here. Oops, not this one. And now I'm going to remove this guy here. And I'm going to look very close inside the battery. In order to do that, I have to make my battery larger in the drawing. Okay, so here you go. Let's make sure we get the grid lines here. like that. Yeah, here you go. And now I'm going to increase the size of the negative terminal as well. Just going to increase like that. I'm going to put a larger spacing between the negative terminal of the battery and the positive terminal of the battery. Okay. And then here you go. So what you have right in here is just like a chemical power plant, right here in between the two terminals. It's just like a chemical power plant. It's a very good model to keep in mind to understand the right? In between the plates, right, of your electrodes of the battery. Let me make it large. Yeah, here you go. I'm gonna also like that. Here you go. I'm not gonna go into the details how a battery is put together, okay? But it's not difficult to come up with a battery. It's not difficult at all. You can use almost any solution out there, especially juices, like lemon juice. You can use apple juice. You can use orange juice. You can use all those juices to make a battery, okay? It's possible to make a battery out of those fruits that we have out there. So it's not, to put together a battery is not something that's difficult, okay? What is difficult is to come up with those industrialized batteries that we have out there that are far more reliable than a battery made out of a lemon, than a battery made of a watermelon, for instance, okay? So what we have here in between is a power plant, is a chemical power plant. Chemical power plant capable of separating the negative charges from the positive ones. That's what you have. Provided the battery still have some energy, the battery will be able to separate the negative charges from the positive ones, okay? Chemical power plant that separates the negative charges from the positive one. That's my valence electron. Valence electron, oops. Valence electron inside the battery. So this force, this chemical power plant is more powerful than the electrostatic force between the positive and negative atoms, okay? So here you go. So we have this valence electron moving from the positive to the negative side of the battery. And once the electron moves to the negative side of the battery, okay, what's going to happen? Now we're going to have the electrostatic force of this negative plate will be able to propel the electron back into the circuit, okay? That's how you have to picture what goes on inside a battery. Let's, okay, once electrons reach the positive terminal of the battery, something interesting happens. If the battery is still charged, if the battery still has, right? It still has some energy, the battery itself will separate these valence electrons from its positive terminal. Okay? A battery is just like a chemical power plant capable of separating the negative charges from the positive ones. Once the valence electrons reach the negative terminal of the battery, comma, these electrons will be propelled back to the circuit, to the electrical circuit, right? Through the electrostatic force. Electrostatic force, okay? And everything starts all over again. That's what you have to keep in mind. 10:30:28 right now. Let's go a little bit more. And now, let me show you. And now you have this idea of electric current, right? Electrons, keep in mind that electrons in motion is what we call an electric current. The idea of the electric current comes from the motion of the electrons. The idea of electric current comes from the motion of the electrons, right? And the idea of current also, this idea of current is also applied. This idea of current is also used to describe, right, the motion of water, right? Like in water current. So the idea of current is a generic term. Current is a generic term that applies to motion of something. Current of people, current of water, current of electrons, right? And now we can start talking about our very first concept that's very important. Okay. Let's go back to our previous concepts. Oh, we started with electric charges. Then I introduce you the idea of electric force. Then I introduce you the idea of electric field, the idea of electric potential. Batteries are source of electric potential. And I told you about an electric circuit. Okay? An electric circuit is a path along which the electrons can move. Okay, just like a circuit of a car, right? And those electrons keep on moving in this closed circuit over and over again. And now we are going to have this idea of electric current. And how is it defined? There's a mathematical definition for an electric current, okay? So electric current is defined in terms of the number of electrons, the numbers of, not exactly electrons, but the number of electric charges, the number, the amount of electric charges that crosses a given cross section of a wire in a given amount of time. Mathematically speaking, that's the definition of the electric current. Okay, mathematical definition. Delta Q over delta T. Okay. If we are dealing, if the charges are just electrons, if the charges are just electrons, comma, then we can here write the above equation as number of electrons times their charge, right? If any electrons, if the charges are just electrons, and we have any electrons crossing a given cross-section area in a given amount of time, a given amount of time, then, right, we can here write the above equation as number of electrons times the electric charge of the electrons divided by delta T is going to be the current. Here we go. What else do we have to know? We have to know the unit of this quantity. Okay, delta Q over delta T is coulombs per second. It's kind of a velocity, right, of charges, right? Number of coulombs per unit of second. This unit is so important in physics. It occurs with so, frequently that we give it a name. We call amperes or amp, and represented by the letter A, by the single letter A. Okay. There are our, DMM, digital multimeter can be used to measure current in a circuit. And let's take a look here of, here you go. Oh, here you go. Here's my copper wire, okay? So we have all sorts of electrons in this copper wire, all sorts of free electrons, valence electrons in this copper wire. Okay, if we apply a potential difference between those two ends of the wire, copper wire, what's going to happen? Those electrons are going to move towards the positive terminal of the battery. Okay, so let's see if I can do better than that. Okay, I'm going to move a little bit so one picture can overlap with the other, right? Let's see if it can. We have it here. That's good, right? Good enough? Okay. So what's happening here? There's more to it. I'm not telling you everything, okay? When you connect this wire here, copper wire, to the battery, what do you have to? We have this electric field that's created inside the wire, okay? And it happens that this electric field is uniform, okay? It's not, I cannot prove it mathematically because there's too much It's very difficult to do that, okay? But you can believe that the electric field inside the wire is going to be uniform. I once saw a paper by one professor that he published. He proved mathematically that in a given wire, the electric field is going to be uniform, but that's no small achievement, okay? It's very difficult to prove that the electric field is uniform inside the wire. So it's better that you just memorize it, okay? And I'm gonna emphasize that, let's see, I'm gonna emphasize the fact that the electric field is uniform inside the wire. And I'm gonna do that just by removing the electrons that are here. Okay, so here you go. So you can see the electric field more easily, right? Here you go. So, and I'm going just to copy those electric field. Oh gosh, I hate that when that happens. Here you go. I'm gonna copy, 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 copy. I copied everything. So the drawing is not as complicated. Now you can see better, right? The electric field vectors inside the metal. Okay? Even though the metal is solid, yeah, we still have an electric field there inside. We still do have an electric field inside. And there is a potential difference here between this end and the other end. Let's say in this case, I said it's 10 volts potential difference. And now that the electric field is inside the copper wire, you can visualize in which direction the charges are going to move, right? A charge subjected to an electric field is going to experience a force, an electric force. Let's see if I have here the electric force here. Oh, here you go. Here's my electric field again. Negative, right, charges, positive charges. Those are the positive charges of the battery. Those are the negative charges of the battery, of the negative terminal of the battery, right? Positive charges of the positive terminal of the battery. Because that is this electric field. To the left, we are going to end up having an electric force. To the right, huh? Do you picture that? And I'm going to remove some of the charge so you do not have too much stuff here. And I'm going to concentrate only on one of the electric charges. Here you go. Electric fields. If you're going to visualize what is happening here, right? My electric field is no longer to be dashed. I'm gonna put it like that. I'm going to move my electron a little bit here to the right, to the left, right? So because the electron here is subjected to this electric field, we are going to have even better. I'm going to put this, this electron right here at the other end. Better this way. Because the electric field is from the right to the left, this electron is going to be subjected to an electric force that is going to be from the left to the right. Okay, and I'm going to put in a different color. Right? And I'm going to get rid of this electric field as well. And here you go. I'm going to label this other vector. Oops, this other vector that I put it here. And very soon we're going to go for our break. Force, red color, right? Electric force, right? That's how you have to picture. Go. And because of this electric force, the electrons are going to move as a set to the right side. Okay, here's the velocity. And then here you go. The electric current is going to be given by the number of electrons that crosses this cross section. It's just like a gate. Think of this cross section as a gate. And then we have this small green man that's capable of watching how many electrons crosses this gate. Okay? That's how electric current is determined. And the number of electrons crossing this gate in the unit of time, in a given unit of time, is going to be the current. Okay, so here we go. And let's take a break before of course we take a break. Let's take a 10. Any questions about that? Keep in mind, right, in order to understand an electric circuit, you have to understand how an atom is put together. In order to understand how an atom, in addition to understand how an atom is put together, you have to understand that an atom has valence electrons. In addition to that, you also, all sorts of important pieces of information, right? And what else? When you put a bunch of atoms together, like in a metal, in a bar of a metal, the valence electrons start to jump from one atom to another one. If you apply an electric force to this bar of metal, all the electrons, all the valence electrons are going to move in a single direction. And you're going to have a current, an electric current. And this electric current is given by the amount of electric charge that crosses a given cross section per the unit of time, per unit of time. That's the idea of the electric current. And now I'm going to take attendance. Let's see how many students we have here so far. 21 students. Lecture today is the 10th of March. Abir, Ahmad, are you there?
Yes, I'm here.
Yeah. Okay. So I guess I heard Abir saying, right? Nestor Alvarado.
Here.
Thank you, Nestor. Okay, next in line here is Monte Ambarshan. Are you there, Monte? I don't see Monte here in my spreadsheet, in my roster. Next is Hasti Amin. Hello, Hasti. Doesn't look like Hasti is here. Next is Isabella Ballestero. Isabella, I don't see Isabella either. Justus Bowden. Okay, thank you. Thank you, Justus. Alexandra Barmistrova.
I'm here.
Thank you, Alexandra. Benjamin Carvajal. Benjamin here, good. Brianna Carrillo. I don't see Brianna here. Doesn't look like Brianna is here. Elizabeth Castellano. Hello, Elizabeth. I see Elizabeth in my roster, in my Zoom roster, but I don't hear from her. Next is Natalia Cordoba. No, I don't see Natalia either. Next is Jacqueline Delgadillo.
I'm here.
Thank you, Jacqueline. Jenny Diaz.
Here.
Thank you, Jenny. Valerie Diaz.
Here.
Thank you. Juan Escalera. I don't see Juan. Bianca Eulaki.
I'm here.
Thank you, Bianca. Dana Gomez.
Here.
Thank you, Dana. Edwin Gonzalez.
Here.
Thank you, Eli Gonzalez.
Here.
Thank you, Manuel Hernandez.
Here, Professor.
Thank you, Samantha Hubert. Doesn't look like Samantha is here. CJ, are you there, CJ? Doesn't look like CJ is here. Luis Leal. I don't see Luis either. Amber Lopez. Are you there, Amber? Doesn't look like Amber is here. Arely Lopez. I don't see Arely either. Genesis. Genesis Lopez.
Here.
Thank you, Genesis. Mary Michaelian.
Here.
Okay. Thank you, Mary. Ramon Olivares. I don't see Ramon. Taylor Thorne. Okay.
I'm here.
Thank you, Taylor. Jeremy Pittman. I don't see Jeremy. Stephanie Ramos.
I'm here.
Stephanie, is that right?
Yeah, I'm right here.
Thank you. Leslie Rios.
Mm-hmm.
Thank you, Jason Strait.
Here.
Thank you, Jason. Gema Torres Navarro.
I'm here, Professor.
Thank you. Let's see how many people we have. Okay. Cannot do that. Okay. Just two students, 25, 27. Wow. What's going on here? Let's see what's going on here. Ah, that's why. Let me fix that. 35, F35. Huh? Oh, yeah. 35. Like that. Okay, 20, 21, 22. Okay, so it's 10:50 right now. Let's take our break. Break from 10:50 a.m. to 11:05 a.m. And I see you in 15 minutes. I'm back here. Okay, so let's do a simple exercise. Simple exercise. Let me see if I can get one of my batteries here. Okay. I'm sharing my screen, right? I'm gonna stop sharing momentaneously my screen. And because I want you to see the battery that I have here. Okay. This is a AA battery, rechargeable one. Let me stop. Let me do something else to my background too here. Here you go. This is my battery here. Okay, AA battery. This one is a rechargeable. I like to use rechargeable batteries. Take a look. Can you see it? This battery here says that it has a charge of milliamps hour. Okay, milliamps hour. Do you see that? Okay. Let me see this other one, if it has anything like that too. It doesn't say. Not every battery has this inscription there, okay? Yeah, for some reason, not every battery, they put the amount of charge. For some reason, I do not know why. It would be correct if everybody would document the amount of charge in the battery. Let's see this other one here that I have. Another one. Yeah, I don't see the charge either. Oh yeah, this one too. This one has rechargeable. This one is 2,500 milliamp hour. The other one is 2,600, right? This Duracell battery is 2,500. So the exercise is related to what you have, what I showed that to you. Okay, simple exercise. Here you go. Some batteries out there have a charge 2,600 milliamp hour. How do I know if it is this milliamp hour? Is that a charge? Is that a unit of charge? Right? You gotta think about that. Is it unit of charge or not? Oh yeah, it is. If you do dimensional analysis, you're going to find out that what you see here is the unit of a charge. Okay, it's not exactly the coulomb, but it is a different type of unit. Okay, and we are going to solve this problem here. And the idea here, what is the charge in coulombs of this battery? What is the charge in coulombs of this battery? And then I'm going to work the solution. Okay. So we start. Okay, we start with the equation for the current. Remember that amperes is the unit for the current, right? Consequently, we can start with the equation for the current to solve this simple exercise. Okay, and what we want to do?
Professor,
we want
you're
to
not
know.
sharing your screen.
Oh yeah, thank you. Let's see. Let me get. That's what happened when I spent so much time. Here we go. Here you go. Now we have it. Some batteries out there have a charge of 2,600 milliamps hour. This part here that you see is a current, right? But then this current is being multiplied by a unit of time. When you multiply the current by the unit of time, you end up with the charge. Okay? So there you go. And you're going to see more clearly in this equation. We want to know what is the charge that your battery holds in coulombs. What's the charge in coulombs, right? So we have to multiply the current by time. If we multiply the current by time, we get the amount of charge. Okay. Well, now the amount of current is just this 2,600 milliamps, right? Or let's say 2.6 amps. That's the amount of current that we have here. 2.6 amps, right? 2.6 amps. And the amount of time here would be the hour. Delta T would be 1 hour. Make sense? And now we can, don't forget that amps is coulombs per second. If we want to get the amount of charge in coulomb, and I'm going to highlight coulomb here, we must have the same unit here. That's going to cancel out with this unit, right? So we can write down that 1 hour is 3,600 seconds. And now we have the second canceling out with seconds. And all you have to do is a simple calculation. That is going to end up being more than 7,200 and less than 10,000. Okay? Just plug in there in your calculator, 2.6 times 3,600, and then we get 9,300. No, wait a minute, 9,360 coulombs. Okay? That's a very simple exercise. One more thing here. I didn't tell you yet. The direction of the flow of current, okay? The convention adopted is the direction of flow, okay, of the, and that's not, that can cause certain confusion, a certain degree of confusion, but it's the direction of flow, not of the negative charges, but of the positive charges, okay? If you were to have positive charges carrying the current, then that would be the correct direction of flow of current, flow of the current. So if we go back here to my circuit, let's see. Even though the charges are moving from the left to the right, the negative charges are moving to the left or to the right. If the charges were positive, they would moving from the right to the left. And the direction of flow of the current in the circuit would be counterclockwise. Okay, that's the direction of flow of the currents. Okay, counterclockwise from the negative to the positive in the battery. Remember that. It's not the direction of flow of the negative charges. By convention, it was stipulated the direction of flow of the current is the direction of flow of the positive charges. Even though the negative charges are the one that carry the current carrying particles, right? The direction is going to be contrary to the negative current, to the negative charges. And there's a reason. The reason is a historical reason. Okay, it's just a historical reason that we never bothered to fix. You know, that at the time of Benjamin Franklin, they didn't know about the electrons and the protons, right? The electrons and the protons were only discovered in the 1800s, in the late 1800s, early 1900s. So back at the time of Benjamin Franklin, people thought that the current was carried by positive charges, not by negative charges. And it became established that the direction of flow of the current would be in the direction of flow of the positive charge. And since the discovery of the electron, nobody bothers to change that convention. Okay? Just a matter of convention. That's the established convention that nobody. This is a convention. This is a convention that was established in the 1700s at a time that nobody knew about the electron. And at the time, it was stated that the current carrying particles were positive, were positively charged. Okay? And the direction of current was dictated in terms of this particle. This type of particle, this type of charge, okay? Like that. And since the discovery of the electron, nobody bothered to change this convention. Okay? Since the discovery, right? The discovery of the electron at that time, right? At that time, nobody knew about the existence of the electron or the proton. If the electron is already difficult to discover, imagine how difficult to discover was the proton, right? And that's what we have for current. I want to tell you something else about, no? Okay, so let's go back to the ideas, right? That we have here. I'm going to introduce you another idea, another important concept in physics, in electricity. So we have charges, we have force, we have field, we have potential, and we have electric circuit, we have an electric current, and then we have something else too. That's called electric resistance. Okay? Electric resistance. Okay, so what is electric resistance? Electric resistance is the electric counterpart of the mechanical friction. Can you remember that? Okay. So when you have the electrons moving inside your wire, right? We have those protons, those nuclei that are attracting those moving electrons. And we also have some non-uniformities in the cable too that slow down the motion of the electron. Can you picture that? Okay, the electrons, they don't move towards the right in a uniform fashion. Actually, those electrons, because you have a force applied to them, those electrons, they are supposed to accelerate under this force, under this uniform force, right? But along the way, what's going to happen to those electrons? They're going to be attracted by positively charged nucleus. Okay, they're going to collide against some non-uniformity in the copper cable. So the motion of the electrons will end up being just like that of a pinball in those pinball games, moving back and forth, okay? Colliding, slowing down, okay? That's another picture that you have. That's another model that you have about the electric circuit. So those electrons, they're moving back and forth, but overall, they're going to move in a single direction. Okay, it's going to be something like that, And if I were to draw the motion of a single electron in this cable, it would be something like that. So here you go. I'm going to get just one electron here. Everything else is going to go. Overall, each of those electrons are being attracted, are moving to the right. The current is to the left. But in reality, their motion is going to be like a type of zigzag path. Okay, which overall is going to be to the right, okay? Colliding with other electrons, colliding with other atoms, and so on, okay? That's the direction of motion, that's how an electron moves. And this velocity from the left to the right, okay, is called the drift velocity. This overall velocity from the left to the right is called the drift velocity. Here he's going to have an instantaneous velocity. Here we are going to have another instantaneous velocity and so on, right? But the drift velocity is going to be uniform. This instantaneous velocity can be accelerated during a small period of time. But overall, we are going to have a drift velocity that's going to be uniform in time. Okay? That's what you have to know about. No, it's not the one I want. I want this one here. Yeah. Okay. Let's write that down. Okay. Due to friction. Since the electrons, the force that powers the electrons in the atom is constant, okay? Let's see, due to the uniform electric field in a wire connected to a circuit, the force applied to the electrons, right, will be uniform. It will be the force applied will be constant. However, a constant force implies that the electrons will be accelerated, okay? Will be accelerated unless you have some other force acting on the electrons, okay? unless you have some other force acting on the electrons. And the reality is exactly that. Exactly that. There is a frictional force also acting in these electrons. These frictional forces, I'm going to put between quotes, okay? This frictional force or force of resistance to the motion, okay? To their motion. This frictional force arises because of the attraction that the nuclei in the wire exerts on the electrons, and also due to known uniformities inside the metal. As a result, the instantaneous motion of the electrons will not be in a single direction, not be in a single direction, but a zigzag path that, on average, ends up being towards the positive polarity of the battery. Okay. Overall, because of the zigzag pattern pass, overall the velocity of the electrons will be uniform on the order of centimeters per second, even though their instantaneous speed will be much higher than that. Okay? The instantaneous speed of the electron is going to be much higher than that. But because of the zigzag pattern, the so-called drift velocity will be on the order of centimeters per second. Because of the zigzag pattern, the overall velocity of the electrons will be uniform, the so-called drift velocity. The so-called drift velocity on the order of centimeters per second. Note that this drift velocity is different from the instantaneous speed, of the electron, which can be much higher than the drift velocity, okay? Than the drift velocity. So that's a picture that you must have Okay? Now, this force of resistance, okay? This force of resistance to the motion of the electrons is encapsulated in the concept of electrical resistance. Okay? And this electrical resistance depends on the following. This electrical resistance depends on the following. One, the length of the wire. Two, the cross-sectional area of the wire. And three, the intrinsic property of the metal the wire is made of. Okay? This intrinsic property is called resistivity. Okay? So that's what we have. So this electrical resistance depends on those three parameters: the length of the wire, okay? And I'm going to write that down here: the cross-section of the wire and an intrinsic property of the metal. Okay? And this intrinsic property is called resistivity. The length of the wire, the larger, here we go, the longer the wire, the more resistance, the larger the resistance, right? The larger the electrical resistance. The larger the cross-sectional area, the lower the electrical resistance. And also what else? The higher the resistivity, comma, the higher the electrical resistance, right? Can you picture that? Okay, the more, why is that? You know, it makes sense, right? To say that the longer the wire, the larger the electrical resistance. Well, why is that? Because the longer the wire, the more resistance the electrons are going to find along their paths. Okay? And the same, and the contrary can be said about the cross-sectional area of the wire. You know, the larger the wire is just like the cars in a very wide freeway. That would be a very good way of comparing an electrical circuit, an electrical cable, with a mechanical equivalent. Okay? So the resistance, so we can write down that the resistance is going to be a function of those parameters, right? The resistance is going to be a function of those three parameters. One, the length of the wire, the cross-section of the wire, and another parameter that is an intrinsic property of the metal that we call the resistivity. And this resistivity we represent by the Greek letter rho. Any questions so far? And then we can go even further than that. we can also state that the resistance is going to be proportional to the length. Here you go, proportional to the length. Inversely proportional to the area. Inversely proportional to the area. And I'm using the area as a prime. There's a reason for that. So I don't mix it up with the symbol for ampere, right? And it's going to be also directly proportional to the resistivity. That's a very good model that works very well. Overall, we can write the following formula. Okay, the formula is going to be something like that. A property of the material, whether it's made of gold, copper, or silver. A geometrical property of the material, that is the length, and another geometrical property of the material, that it is an area. Okay? Can you remember that? We can even take a look at the resistivity of some materials out there. Let's take a look. We have that in Wikipedia. Let's take a look at some numerical values of the resistivity. Here you go, common symbols, rho. Let's take a look here. Here you go, the same thing I'm telling you, all right? Here you go, rho L over A. And we have a table here for resistivity. Huh, they don't have a table for resistivity here. What a shame. Oh, yeah, they do have. Okay, here you go. Remember that I told you copper is a very good conductor? It's a very good conductor. See, you know, you should expect that its conductivity would be very high compared to the other ones. If the conductivity is higher, it means that its resistivity is going to be among the lowest one, okay? And that's the unit of resistivity. The unit of resistivity is ohm times meter. And look what those values, what we have values there. Here you go. Conductivity, silver is 63, copper is 59. Here's the annealed copper. It's slightly different, it's slightly lower. And you can go through those numbers and you're going to see that just silver and copper have the best conductivities, right? You don't see any other one, right? You have a number here, 6.7, but the 6.7 is times 10 to the fifth. Okay? So those values have been measured. And the conductivity is just the inverse of the resistivity. Okay? So the resistivity of a material is related to its conductivity. According to the following formula. You go, you know, sigma. Conductivity is represented by the letter sigma. And it's 1 divided by rho, okay? Don't forget, this is intrinsic to the material. It doesn't matter. So now we can start playing with this equation, okay? Suppose that you have two copper wires. This one is made of copper. This one is also made of copper. One is longer than the other one. right? Which one is going to have the higher resistance? Okay, which one is going to have the higher resistance? They're made of the same material. Obviously, it's going to be this one because it's longer, right? What about here? Two copper wires again, but one is thinner than the other one. Which one is going to have the highest resistance? This one right in here. Okay, lower resistance, higher resistance here. Lower resistance because it's thicker. You have, just as though you have several lanes here for the electrons to flow. Okay, and consequently, the resistance is going to be lower for that. What else do we need to know? Okay. So here we go. Going back here. Electrical resistance. You already know there's another equation for the electrical resistance that you have to memorize, okay? It's possible to derive it, and it is a consequence that is, there is another equation that relates the resistance with some other parameters, okay? Remember, by the same token that the capacitance is written, I'm going to make a parallel here. In terms of the charge and voltage, do you remember that? Here you go. The capacitance, right? Capacitance can be written in terms of the charge and the voltage, which by the way, we'll also learn that ultimately becomes a function of the geometrical parameters of the capacitor. By the same token that we have this relationship, right? We also saw above that the resistance also depends on the geometrical parameters of the resistor. Right? We saw that right in here. Geometrical parameter here, geometrical parameter here, right? But then there is one more. But then there is one more equation. But then there is one more equation that parallels the definition of capacitance. Parallels the definition of capacitance. Okay? And there's one more, but there is one more equation for the resistance. There is one more equation for the resistance that parallels the definition of capacitance. If the capacitance is given by the charge divided by the voltage, okay, there is a so-called law there is a law, I'm going to put it between quotes, okay, in electricity that relates the resistance with the current and the voltage, the so-called Ohm's law. Ohm's law. And Ohm's law is written in the following way. Okay? V equal to Ri. Let's not forget that I is also delta Q over, right? Delta T, like that. if C is equal to Q over delta V, R, I'm going to write this equation in terms of R. Okay, R is going to be given in terms of V divided by delta Q over delta T. Okay? See, we have V here, we have V here, right? We have Q here, we also have Q here. The only difference is that those terms appear inverted. That's the only difference. That's why I like to define a parameter that I call incapacitance, okay? Incapacitance that I write as being the inverse of the capacitance. Oops. The so-called incapacitance Q now follows just like Ohm's law. The incapacitance is directly proportional to V, and I'm going to change it to a red color, right? The resistance is also proportional to V. The incapacitance is inversely proportional to Q. And the resistance is also inversely proportional to Q. This is no coincidence, okay, folks? This is no coincidence. And I'm going to put it in different colors, right? Instead of red, I'm going to put it in blue. There you go. This is no coincidence. We defined it in this way. Scientists define that for a good reason. Okay. Okay, the bottom. Am I sharing the screen, right? Yeah, I'm sharing the screen. 1109, yeah. Okay. So now, and remember, be reminded, right? Be reminded that we have 4 important elements in electricity and electronics. Remember that? I told you that. Capacitor is the first of them. The second one is the resistor, and we're studying the resistor right now. The other one is the inductor, and the last one is the transistor. And look what we are getting, the capacitor, or let's say the incapacitor, the incapacitance, right, is directly proportional to V, so is the resistance, right? The incapacitance is inversely proportional to Q, and so is the resistance, right? And this type of pattern, we are going to find with the inductor as well later on. Okay, we are going to see that with the inductor as well. And can even tell you right now that the equation for the inductor, not the inductor, but the inductance, right? There is capacitance, resistance, and inductance, right? Or even better, incapacitance, resistance, and then we have this other parameter called the inductance. It follows quite the same pattern. And the inductance is usually represented by a fancy L. Let's see if I can find this fancy L here. Greek letter. I will have to invent it. Greek letter, basic mass. Let's see, operators. Maybe an operator. No, I don't see it. It's a fancy L. Let's see, negated. Unfortunately, I can't find it. This fancy L. I have to invent another one. I have to use another one. Later on, when we start talking about magnetism, let's see if it's here. Oh, yeah, here you go. I found it. Yeah, that's the fancy L. It's going to be proportional to V, but it's going to be inversely proportional to Q as well. But it's going to be the Q in terms of the current I, okay? You see the pattern that we're getting here is a delta of a delta. Let's see here. Delta Q over delta T. Okay? Directly proportional to V, inversely proportional to Q. Okay? So that's the next device, next important device, electric resistance. There are two equations for the electric resistance that you saw, right? One is given by the geometrical parameters and the other is given by Ohm's law, which is, here you go, V over I. V, I'm going to put I here to simplify the equation, or V equal to Ri. It's 11:52 right now. Any questions about that? We're going to do some examples. It's 11:53. I'd like to take a break. Okay. And oh, by the way, I gotta tell you about, before we go to the break, let me tell you about the unit, right, of the resistance. Let me tell you, the unit of resistance can be found by using Ohm's law, okay? It's easier. So to use Ohm's law to find the unit of resistance. So it's going to be the unit of V divided by the unit of I. The unit of V is the volts. The unit of I is the amps. That's the unit of resistance. This unit of resistance shows up so frequently in physics that we give another name. We call it the ohms. Ohms. Okay? Ohm, represented by the capital omega, by the letter capital omega. And now from this relationship, you can find out what's going to be the unit of rho, right? Here you go. All you gotta do is to do dimension analysis, 11:54. Let's go for another minute before our break, right? So here you go. A prime divided by L, that's the relation for rho. And now that we have the relation for rho, we can come up with a dimensional analysis to find out the unit of rho. The unit of rho is going to be the unit of resistance. What happened here? Okay, the unit of resistance times the unit of area divided by the unit of length. And we get exactly what you saw in that table of resistivity. The unit of resistivity is the ohm times meter. Okay. Now we can go for a break. Any questions? Break from 11:55 a.m. to 12:10 p.m. Okay. I see you in 15 minutes. I'm back here. 12:10. We're going to have another 40 minutes to go. And okay, so we have we are getting our staff together to learn about circuits. Okay, so let's list our concepts right in here. In addition to the concept of electrical resistance, the current, we also have resistivity, right? Electrical resistivity. Is this CVT? We can place that right in here. And so let's start with some examples. Okay, so even better, let's try an example from the book. This one here, electromotive force, Ohm's law, see? Electromotive force, Ohm's law. You know, keep in mind that I elaborated much more than the book, okay? When I start talking about electric circuits, you know, all that elaboration that I put forward for you is not gonna be in the book. But Ohm's law is in the book. Why is it not displayed? Let's see here, why it's not displayed. Okay, good, now it's displayed. Okay, so here go the same drawings that I had, right? Here's the battery, symbol of the battery. Here's another battery, same symbol. Okay. Ohm's law V equal Ri. And let's take a look at this example. Let's see the first example that we have in the book, a pocket calculator. Okay, we did something similar, right? Okay, the battery pack of we did a similar example than the one in the book. Ohm's law, flashlight. The filament in a light bulb is a resistor in the form of a thin piece of wire. The wire becomes hot enough to emit light because the current in it. Interactive figure shows 20.5, this one here, yeah. Shows a flashlight that uses 1.5 volt batteries. Effectively a single two 1.5 volt batteries. Effectively a single 3 volt battery. When you combine two batteries, that, you know, if you combine them in a proper way, you can increase the voltage. So that's what they did here. They got two batteries and they connect the battery in series, okay? One battery here, another battery here. You increase the voltage in the battery to provide a current of 0.4 amps in the filament. Determine the resistance of the glowing filament. Okay, so this type of configuration is we display like something like that. Okay, so here it can be 3 volts, right? Here's the circuit diagram of your flashlight. Here you have the two batteries that are represented by this symbol that you see right in here. And here we have the filament. Okay? Going back to and then we have this current flowing counterclockwise. Let's go back to the problem again, the example again. Let's see, we have what? The wire becomes hot enough. Show the flashlight, we have V, 3 volts, and we have the current 0.4 amps. What is the resistance of the glowing filament? Okay, simple enough. So I'm going to write down here my example. Example, circuit with a single resistor. A circuit with a single resistor can be exemplified by a flashlight with a bulb, the filament, and two batteries connected in series. Two 1.5 volt batteries, two 1.5 volts batteries connected in series. If the current is 0.4 amps and the voltage is 3 volts, right? What is the resistance of the flashlight bulb? And Ohm's law. That's going to be one of the simplest problems that we'll ever see that applies Ohm's law. Solution. Okay, so let's start with Ohm's law. E equal to Ri. Ri. Okay. You already know that V is 3 volts. You know that I is 0.4 amps. Substitute that above. Straightforward, right? Oops. 3 volts here. I is 0.4 amps. And then you solve for R. Three volts divided by 0.4 A. Like that. And what we end up getting here is 7.5 ohms. Okay. 3/4 is 3.75, right? 3/4 is 3 divided by 4 is 0.75. 3 divided by 0.4 must be 10 times 0.75, which is 7.5. Is that what the book says? Let's take a look. Yeah, 7.5 ohms. Like I said, that's going to be one of the simplest problems you ever see applying Ohm's law. And then you have more difficult problems, okay? More difficult problems that relates to a circuit, to circuits that have more elements, okay? So here you go. Here is one, here's the problem that we just did, right? One resistor, electric circuit with one resistor. Then we have electric circuit with two resistors. Okay, here you go. Electric circuit is two resistors. So given D, R1 and R2, find I. Okay. We can do this example as well. It's a little bit more complicated than you saw before. Okay. Circuit with two resistors connected in series to a source of electromotive force B. Find the current. Okay. And I'm going to copy and paste right in here. Okay, so here you go. The current is moving in this counterclockwise direction. And what you have to know? You have to know that as the current goes by the first resistor, it's going to lose some electric potential that I'm going to call V1. Okay, that's what the resistor is there for. The resistor is there to take away energy from the electrons. Okay? So as the electron goes through this resistor, it lost electric potential V1. Okay? It starts with the electric potential of V, loses V1, and goes through the second one. It's going to lose V2. By conservation of energy, V1 plus V2 must be equal to V. Okay, and all those wires that you see here in between the electric source, the power source, is considered to have negligible resistance. Okay? And then, look, we can, once the charges goes through the first resistor, it's going to lose a given amount of electric potential. And this amount of electric potential is going to be given by V1 equal to R1, I1. We know R1. We do not know I1. We do not know V1. Okay? But then when it goes through the second resistor, it's going to lose some more energy, some more electric potential, which is going to be R2, I2. Okay? Due to conservation of energy, we must have that V1 plus V is going to be, V1 plus V2 is going to be equal to V. That's how you have to solve this problem. And then there's an easier way of doing that too, okay? I'll give you a simpler way of solving this problem. And now we are going to have three equations. Three unknowns, four unknowns, right? V1, V2, I1, I2. Okay? Note, the first equation. The first equation comes from the principle of conservation of energy. The other two equations come from Ohm's law. Okay? Notice that we have three equations and four unknowns. Because the number of unknowns is larger than the number of equations, we cannot solve this problem. Let's see, someone left a message here. Sorry if I didn't see the message earlier. It's supposed to be A over L. Let me see, 12:11, right? 10 minutes ago. Tell me where, Valerie, you're talking about A over L. Tell me where. I'm scrolling up. Just
It was a little bit before the week when you were
Before?
writing the equation.
Am
A
I
little
going in the
bit
right
more.
direction?
Yeah,
Is that the one here?
right there.
Yeah, I put
A
A
over L.
prime. I put A prime, okay? Why did I put A prime? There's a reason why I put A prime. Do you remember? Huh? A, I reserve for amperes, right? Amperes, for the unit of ampere. But A prime, I reserve for area of the wire, okay? So to distinguish one from the other. That's why I put A prime instead of A. Okay. So here is area.
Yes, I understand. Could you scroll a little bit up? Because I thought it was supposed to be length over
It is
area.
here, right? Let's see. Oh no, this one is
But
right.
then it's a little bit
Go up more.
or right there where you highlighted it. I
Yeah.
was just wondering why it's length over area in the third equation.
Yeah, remember the resistance increases with the length, right? And decreases with the area, right?
Mhm.
L over A prime. Did I say that before? I'm quite sure I did that before. Let's see. Oh yeah, see, I did the same before, right? It's inversely proportional to the area. See that? The larger the diameter of your wire, the easier it is for the electrons to go through the wire. Consequently, the resistance is going to be lower. Okay? That's what you have to memorize. And maybe, let's see. Now, do you see this other one here?
Yes.
Is this thing in agreement with that? Yes or no? Right? That's what you have to ask yourself. Is this equation in agreement with this one?
Yes.
Yeah, because I'm here I'm solving for rho, right? And here I'm solving for r. They are in agreement. Okay, so this equation here is the same as this equation, but just written in a different format. Okay, but don't forget the resistance goes down with the area. The larger the area, the less than resistance. Okay, let's go back to our. Okay, so here we go. Now, the first equation comes from the principle of conservation of energy, right? The other two equations come from Ohm's law. Notice that we have 3 equations and 4 unknowns because the number of unknowns is larger than is greater, right? It's greater than the number of equations. We cannot solve this set of equations. In other words, we need one or more equations. One or more equations. We need one or more equations. And what is this equation that we need? Okay. We are going to look at this drawing here. Okay. So here you go. I told you that I1 is the current through this resistor. And I also told you that I2 is the current through this resistor. I also labeled that we have a current I coming out of the battery. Okay. And what is I? I is the amount of charge passing through this cross section here of this wire. Okay. And I1 too is the amount of charge that passes through one of the cross sections of your resistor. Okay. Similarly, I2 is the amount of charge passing through one of the cross sections of the resistor number 2. Because because you must have conservation of electric charges, okay? The number of electric charges that pass per unit of time here must be equal to the amount of charge that pass through this point here and this point here. The current pass through resistor 1 and through resistor 2 must be the same as the current coming out from the battery, okay? So now we can get another equation. Note C that due to conservation of charge, right? The amount of charges exiting the battery per unit of time must be the same as the number of charges passing through either resistor in a unit of time. In other words, what do we have? We have that I1 must be equal to I, and I2 must be equal to I as well. Okay? And now we have 1, 2, 3, 4, 5 equations. Here you go. 2 more equations. Let's count how many unknowns. 5 equations. The following unknowns. Unknowns. I1, I2, V1, V2. Oh, you have I2. I is an unknown as well. Okay. V and R are known because I provided you at the beginning of the problem. Okay. And then we have subscript. I1 goes here, I1 goes here too. And I'm going to place I1 here, but then I'm going to erase it and make it I2. And I will copy this I2 and place it here. 5 unknowns. 5 unknowns for 5 equations. Okay? We can now solve this problem. I'm going to use this one right here. Okay? Copy and paste. Using the first one, we get this value. Using the second equation, we get this new equation. Since I already used the first 2 equations, I can eliminate them. And now we have, see, now we have 3 equations for 3 unknowns. And what are those unknowns? The unknowns are V1, V2, and I. We are progressing in the solution of our problem. What was 5 unknowns? Now it became 3 unknowns. And what do we want to do? We want to find I. That's what we want to do, right? We want to find I. Let's see how you can do it. In order to find I, we have to eliminate V1 and V2, okay? To eliminate V1 and V2, we have to substitute V1 here and V2 here, okay? So here you go. I will copy and paste it. V1. Here you go. Okay, V1 goes here. V2 goes here. Can I do better than that? Yes, I can put I in evidence. Okay, I can put I in evidence. And now I have this brand new equation. And we can solve for I. Okay, what was 3 equations now became a single equation with a single unknown, right? And the unknown is I. So to finally solve the problem, we have I equal to V divided by R1 plus R2. Like that. We're done solving the problem with 3 resistors. Okay. Those, this configuration that you see right in here is a configuration that states that 2 resistors in series, okay? We have 2 resistors in series behave as though they are a single resistor with an equivalent resistance of R1 plus R2, okay? That's the first thing, the first thing that you should know to solve this problem more quickly. Note that the 2 resistors are in series, one after another, okay? 2 resistors in series end up behaving like a single resistor with an equivalent resistance given by, okay, here you go. I'll copy that like that. Equivalent resistance R1 plus R2. R1 plus R2. So if you have a circuit just like that, if you have a circuit just like that, you can redraw it in this way. Okay, let me erase this one. You don't need that, it's too much stuff. And we can redraw it like that. Okay, so here you go. R1 plus R2, right? Can be redrawn as a circuit with a single resistance. Okay. That's what we call the equivalent resistance. And I'm gonna copy and paste here. Okay, going back, here you go, 2 resistors. Those 2 resistors combined behave just like a single resistor with the resistance summed up, okay? And that's the case for resistors in series. Let's see how we have in the book. 1240, we have 10 more minutes to go. Resistance and resistivity we covered. Okay, here you go. Here's a table of resistivities for different metals. Okay. Next, electric power. Let's see, does he have electric circuits with more resistance? We didn't cover electric power yet. Alternating current. He likes to cover alternating current at this point. I prefer to cover later on. This is chapter 20. Electric power, then it's series wiring. Okay, I'm doing that. Series wiring. Series wiring, okay? And then this series wiring happens, behaves not just for 2 resistors, but has the same behavior for n resistors, okay? So I'm gonna write down here for you. For n resistors in series, comma, the equivalent resistance is given by like that. I equal to 1 until n. I. Okay? Like that. Let's take a look at the book again. You can have the same type of thing with capacitors, okay? You can have capacitors in parallel, in series, and another way of connecting capacitors is in parallel as well. We go and parallel wiring. Okay. Let's show you how parallel wiring works. Okay, series. Okay. Circuits with 2 resistors in parallel. Here you go. That's a circuit with 2 resistors in parallel. When you have 2 resistors in parallel, the current will be different. Okay? But the voltage will be the same. Okay? Because this point here is the same as this point here. There is no loss in energy for the electron that goes through this wiring here because the resistance is negligible. Okay? So those 2 resistors has the same electric potential. That's what you have to know. Okay? And when you combine this, those 2 resistors in parallel, we're going to have a current flowing through the resistor 1 that's going to be different from the current flowing through the resistor 2. But the electric potential is going to be the same. That's the important thing that you have to have in mind. Those 2 resistors combined become an equivalent resistance. And there is a different equation that we have for this equivalent resistance. Okay, so here you go. I'm going to put it here. For resistors in series, comma, for 2 or more resistors in series, comma, the electric potential across each resistor will be different, but the current will be the same. Okay? We can even start building up a table. What time is that? 6 more minutes to go. Okay, so here you go. So I'm going to I'll leave capacitors for later. Okay. Circuits that are in series the voltage is different. It's different, but the summation of the voltage is going to be equal to the net voltage V. And the current is the same. When we have circuits in parallel, it is exactly the opposite. Can you memorize that easily? Okay. The voltage is going to be the same, but the net current is going to be the sum through the current of the currents flowing through each resistor. Okay. However, for 2 or more resistors in parallel, the electric potential will be the same, but the current will be different. More specifically, it will be the sum of the currents of each of the currents going through each individual resistor. Okay, and it's going to be the same here. The electric potential will be different. More specifically, the net current, the one that leaves the battery, will be the sum of the current going through each resistor. And here's the same thing, the electric potential, more specifically, comma, the net voltage, the one leaving the battery, provided, right? Provided by the battery, will be the sum of the voltages applied to each individual resistor. However, the current will be the same. However, the current will be the same. Those two paragraphs are emphasized here in this table for resistors, right? Then later on, for resistors, later on we are going to look into that for capacitors in parallel and capacitors in series for resistors. We have 2 more minutes to go. Okay. Oh, there's one more thing that I want to tell you. For resistors in series, let's see here. I can also, and I'm gonna do the same for equivalent resistance. Equivalent resistance. Equivalent resistance. Okay. For circuits in series and parallel. And you know what? I can put everything here in a single table. Yeah. And then I'm going to write that down. Equivalent resistance. Okay, like that. Equivalent resistance, and 1 more minute to go. I guess I can finish it before 1 minute. I'm going to adjust this table here. Equivalent resistance, and that would be written like that. Okay. In series, okay, the equivalent resistance is going to be the summation of each resistance separately. What about in parallel? In parallel is going to be the inverse. And I'm not kidding. When I say that it's going to be the inverse, I'm not kidding, okay? And you're going to understand exactly what I mean about the inverse. The inverse is exactly the mathematical equation for the inverse. And that can be proven using Ohm's law, okay? The inverse of the equivalent resistance must be equal to the summation of the inverse of each resistance separately, okay? I can erase that. I don't need that. It's 12:50. Next time I'm going to do some more examples, how you can calculate the equivalent resistance and how you can get also the current and other parameters. Okay? Any questions about that? So I see you soon. So I see you the day after tomorrow. Thank you for being here.
Thank you, Professor.
Have a good one, Professor. Take care.
Thank you,
Professor.
Hello, Professor, are you there?
Yeah, wait a minute. Let me finish. Let me stop here the recording.